Okay, so we're going to tackle a related rates problem here. We've seen this back in chapter 2. It comes up again in chapter 3. We'll continue to see problems like these throughout the year. The scenario is we have an ice cream cone, and here's the picture of that cone, 5 inches high, 2 inches in diameter, not radius. So I'll make sure to indicate that was the diameter. And is leaking from the bottom at a rate of 1/3 cubic inches per minute. So when we see cubic, we automatically know that that is a unit of volume in this case. And so since it is a rate of change, it would be the rate of change of volume with respect to time. So dV dt would be 1/3. Or specifically negative 1/3 here if we want, because it is actually leaking, so it is changing, it is decreasing. We want to know the rate at which the height is changing when the height is 3 inches. So that means that we are solving for dH dt. Now we look at our equation. Volume is written with respect to the radius and the height, not time. So that tells us that when we do our differentiation, it needs to be implicit. We also see that we're going to have to do a product rule because we have the product of r squared and h. The problem with that is that we have no value for dr dt. Now, we've got two ways to tackle that. First, and generally the easiest way, would be to recognize that the relationship between the radius and the height, since the diameter is 2, the radius would be 1 to 5. So if we take the radius divided by the height, right, that would be 1/5, or the radius is 1/5 the height. And that relationship would carry through from top to bottom of the cone. So the easiest way to deal with this is to substitute. I'll write the 1/3 pi as pi over 3. 1/5 h for the r. So I'll write that actually as h over 5 squared times h. And when we square this, we get h squared. That's 25. So pi over 3 times the 1/25. Right, would be pi over 75, and then h squared times h would be h cubed. An alternative way to deal with this would have been to use the product rule, and then we could substitute or determine from here that dr dt was 1/5 dh dt, and then you could have done that substitution for dr dt here. But I think this is the easier of the substitutions. So now we're solving for dH dt. So if we take the derivative of volume with respect to time, right, we have pi over 75. This would be 3h squared. And then doing the chain rule, dH dt. And dH dt again is the variable we're solving for. They tell us that h is 3 and that dV dt is negative 1/3. So we'll make those substitutions. And so that would be 27. 3 times 3 squared, so 27 pi over 75 dH dt. And we will multiply both sides. That pi should have been in the denominator. Multiply both sides by the reciprocal. Anything multiplied times its reciprocal is 1. And so we end up with a negative. That would be negative 25 over 27 pi. And then we want to make sure we have our units. We are in inches and minutes. So we have negative 25 over 27 pi inches per second. That's a linear unit. And there's our solution. Now, there is an alternative way. It would have been a little bit longer. But if we have done the product rule, taking the derivative, dv dt, will factor out the pi over 3 here for now. We would have 2r dr dt times h plus r squared times dh dt. So we could substitute the negative 1/3 there for the dv dt. We would have to figure out what r was. We would use that proportion, right? When h was 3, r would be 3/5. You would have your, for dr dt, you could substitute 1/50 h dt. And so you can see this is certainly doable. Not that it is complicated algebra, but it certainly is a few more steps than doing the initial substitution.